Hey everybody, Lars here. It's been a while. We've had spring break. We had the NCAA basketball tournament. And today I'm sitting at home because it is a snow day. It's 3 o'clock on Wednesday. Got up, got some email done, did some stuff. No rest for the wicked. Still sitting here working. But I haven't gone out and done my first round of shoveling yet, so I'm going to have to go out and shovel a little bit later on. But first, we got to get back in the swing of things. Snow put us back. We're still in pretty good shape because the end of this unit, I believe, is next Thursday. I'm still going to get you all your resources a week before the assignment is due. I will drop the assignment either later on tonight or tomorrow. It's not that bad. I give you some code, and you just have to work with it. So like I think I've told you before, Unit 4 isn't crazy hard. It's kind of a rest in between Unit 3 and Unit 5. We'll do some announcements at the end, and I'll get to some other stuff. And I want this, my deal, my pull is I want to make sure you get enough so that you understand the topic, but I don't want to sit here and talk for 45 minutes and bore the hell out of you. So hopefully this is going to be a quick one, but let's go and take a look at it. Today, really, we're not going to do anything about sorting and searching. We're not going to do anything about Big O. What we're going to talk about today is a topic called recursion. And recursion in computer science circles is often looked upon as if it's super difficult. And it's really not at the end of the day. It's not that crazy a topic to wrap your head around. There's a little story behind how I teach it. But the first thing I'm going to do is let's go to the browser and check out the recursion page on Wikipedia. Because what you find is it's not recursion doesn't relate to just computer science. You can see that Drost Cocoa can was one of the first examples of it in media. You can see the Drost can shows a picture of the nun with a Drost can with her holding the tray, with a Drost can with her holding the tray, and blah, 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 blah. It goes down and down and down and down. That's an example of recursion. At the end of the day, recursion, simply put, is something that refers to itself. You'll see down here, there's formal definitions for recursion. You can see the snake. There's also Escher paintings. Got a couple. One here. The stairs is recursive. It refers to itself, and it goes in a weird way that isn't really possible. One of my favorites has always been that this was copied with Legos. So I always thought that was pretty neat, so I always show people that. You can see down here there's a recipe for sourdough, and the recipe calls for a piece of sourdough from the previous time you made it, which begs the question, what happened the first time you made it? But that almost, in the culinary sense, deals with recursion. But when we talk about computer science and math, we get to Sierpinski's triangle, and we're going to look at recursion, and at the end of the day, you're going to say, oh, wow, that's great, wonderful, why the hell do I care? And what you're going to find is that a lot of data structures in computer science lend themselves to being attacked recursively. And you're going to see that it's very useful down the line. And it's sublimely clever for solving certain problems where you have lists that get smaller in natural ways. And you're going to see what I'm talking about when we get into it. This is my little spiel. When we teach computer science at university, and it happened to me when I was 19 years old, is Intro to Computer Science. You learn how to program, but along the way you get sorting and searching. You learn about recursion. You learn about a little bit of Big O. You've heard that story before because Unit 4 is where I reintroduce all those things. But recursion is usually taught, and the first example you'll see is one of two things. One is to produce the Fibonacci sequence, 1, 1, 2, 3, 5, 8, 13. And the other is to do factorial. Now, factorial is a number multiplied down the line, meaning that if I want factorial 5, I go 5 times 4 times 3 times 2 times 1. Okay? That equals 120, I think. All right? So my issue with this is that if you're a 19-year-old student, and especially if you're just a regular Joe or Jane like I was just a regular guy. I was no great shakes. You may not have seen Fibonacci or factorial before. You're taught recursion. So instantly, you relate those two things to recursion. Okay? And you don't realize that recursion is a technique that can be applied to a whole bunch of other things that you know how to do already. You think of it as, oh, that's that technique where I do Fibonacci, or oh, that's how I do factorial. So when I do recursion, I don't want to do that. I want to show you how recursion can attack problems that you know how to solve. So what I usually do is I do an example of just adding, just getting a sum. It's a special kind of sum because what I'm going to do is we're going to write a function where if I give you 5, it's going to give you the answer 5 plus 4 plus 3 plus 2 plus 1. Okay, so let's do that, you know. Let's go right ahead and do that here. I already whipped up some code for us, not really. So just very simply, I'm going to create a function called mySum. I'm going to take an argument n, and I'm going to say if, and don't worry about understanding it now. We'll trace through this a bazillion times, so you got no worries. And I'm going to say if n is equivalent to 1, I want to return 1. Else, and this is where the tricky part is that correct? Yes, it is. Return n plus mySum. Now, I'm creating this function, but I'm referring to it as I'm doing it. So this is the weird part. mySum n minus 1. Okay? Right here, I'm referring to what I just wrote. And I'm going to call it again, which some people find to be a little weird and a little odd. And first thing we're going to do is see if it works. So let's do print mySum, and we'll just do 5. And maybe if it's at z and there, things won't work. All right, so I'm going to save, and I'm going to run. Hey, look at that. It worked. All right, let's get a little setup here where I can show you things on the screen and you can see everything. That should be good enough right there. Maybe not. Always something. All right. So what happened here? I created a function. It got stored in memory. Comment. First thing we run a lot of times is actually the last line of the program. Print the result of mySum of 5. So we come up here, mySum 5. Okay. Is n equal to 1? No, it's 5. Else, return 5 plus mySum n minus 1, which is 4. So now I'm going to run the same thing, but I'm going to do it for 4. Now, naturally, as you trace through code in your mind, you stay on the page. So what most people would do right there is say, okay, mySum of 4, blah, 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 come up here and run through it again. But that creates problems because then all of a sudden you've got 4 for this, and well, didn't I make that 5 before, and blah blah blah. The key is this, and you're going to see later when I trace things in a different way. You're not using this one copy of the function. You come in with a 5 equal to 1, no. Else return 5 plus mySum 4. What you do is you get a brand new copy of it, which sits in memory. So think of it as a whole new copy of that function. Don't think of it as sitting in the same space and changing variables and doing all that. That's where people get confused. That's where you fall down the rabbit hole. Just think of it as a brand new copy sitting off here to the side. Because that's exactly what's happening. That's exactly what's happening in memory. You've got that function defined. Hey, I need mySum. Brand new copy. Brand new blank copy with just that one variable. And now you sent it with 4. So what do? I come up here to my brand new copy. mySum of 4, is it equal to 1? No. Else return 4 plus mySum of 3. You see, we're saving the value, and then we're calling it again. Saving the value, calling it again. Then, when we get to the end, you're going to say mySum of 1. Is n equal to 1? Yes. And I return a 1. And that's what's called the tail condition. And that's going to get us going boom, 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 back up the stack. Because when I return 1, it's going to return to this. So then it's going to be added to 2. And then return 3 to what? The thing that called it with 4. So now all of a sudden this is going to return 3, and it's going to be added to 4. And that's going to be returned to the one that called it with 5. Okay? So then that's going to come back and come back. And it adds all the digits up because I've got a plus operation here. And it prints up the thing for the digits. Let's do 6. And you'll see it'll come back 21. Because now it's got a 6 to it. Okay? Hold on, let me make this a little larger so that y doesn't sit down there. All right? Now, that's how you do addition or a sum. Now, I showed you that because you already know how to do this the regular way. So now I'm showing you a different way of doing something you know how to do already. So now the contrast or the variation is with the technique, which is what I want. It's what I want to show you, okay? I don't want to show you an operation you've never seen before. If you've never seen Fibonacci before, you might say, oh, that's neat. Oh, hey, they use that as a password, blah, blah, blah. I can tell you 2 different labs at Rutgers University that use the Fibonacci sequence for a password. I'm not going to tell you where they are because I don't want to think them. But scientists like that. They think that's clever when you use Fibonacci. Fibonacci appears in nature all over the place, actually. As usual, I digress, and I'm watching the snow fall, and I'm too old and fat to shovel. Like I'm going to have to shovel later. Come see me in the hospital when I'm laying there with tubes stuck in me and getting fed shakes through a straw, which would probably be good for me. Can you optionally get your jaw wired shut? That's what I need so I can stop eating. I actually got spaghetti for tonight. I always have spaghetti in the snow. Nice hot pasta meal. I'm really digressing. All right, we're going to do one quick thing with this. What if we took this, begink, and changed the operation to multiplication? Now, all of a sudden, we have factorial, and it's 720. And now, all of a sudden, we're doing what I got shown when I was a little kid. All right? I'm going to change it back. And what you'd want to do is you'd want to change the labeling. You'd want to say my factorial. But that's all you have to do. That's the operation right there. Pull back the top of the list, then go do the same thing with a sublist. Run it again. Pull back the top of the list, run it again with a sublist until you hit the tail condition, you hit the end. Okay? One last thing I'm going to tell you in this particular case, and I still don't know how it happens. And this is a good little thing because if you're watching the videos, you're going to catch a break. I'll tell you right now, the Unit 4 quiz, I'm going to ask you to code a recursive function, okay? And half of you, and I don't know where you're getting it from, I hope you're not copying it from your friends, will create a tail condition where n is equal to 0, okay? Which just boggles my mind. Okay, watch this, though. Watch. I'm going to turn that back to plus, and we're going to test it with 6. So it should be 21, right? So we do that. It says 21. Okay, we're in pretty good shape. Now, what if I change my tail condition from 1 to 0? Okay? What do you think is going to happen? Watch. Saying, oh, 22. How did that happen? Oh, because it's, never mind. I need to leave it multiplication. That's interesting. Because then you add the 1. Interesting. I do. Why would it add the 1 though? Return 1. Oh, because I do it twice. Never mind. With multiplication, when I run it, I get 720. If I made it a 1 again, what do I get? 720. It's the same thing. Because with multiplication, 1's the identity. Okay? So you can, instead of 1, have a 0, and the code works. Okay? The problem is that it's inefficient because you're going an extra cycle. You're multiplying by 1. There's never any reason to multiply by 1. Never any reason to multiply by 1. Think about it. Why? Why would you do it? Okay? If you get to a point where you're multiplying by 1, there's no... Why? You already have what you need. No reason to multiply by 1. Okay? That said, I will get a whole bunch of answers that will recurse down to 0. It's 1. The tail condition should be 1. All right? You heard it here first. All right. You got no worries because I am going to take my sum and I am going to put it on our Sakai site so you don't have any worries. But we're not done because I usually show people addition, but I also show people multiplication. So I have multiplication recursion done right here. And I multiply 3 times 5, Actually, we're going to shrink that down, and I'm going to do 3 times 3. You're going to see why in a minute. And I run mult 3 times 3, and then I print A. So when I do that, down here, you can see I get 9. Let's get a fresh. Yeah, stay that wide. That's fine. All right. So you can see I called A. Give me the result of my mult 3, 3. So let's come up here. My mult num 3 times 3 is times equivalent to 1. No. So else return num, which is 3, plus my mult 3 times minus 1, which is 2. So now it gets called again, fresh copy, with 3 and then a 2. Now you see it's confusing using the same thing. So with the magic of GIMP and Camtasia, we're going to do it right here. Okay? So forgive me, but sometimes I have trouble drawing numbers. Hopefully we won't. We have my mult right here. I'm going to do 3. And 3. All right. Times equal to 1. No, it's not. It's 3. Else, return num. What's num? 3. My mult num, which is 3. Times minus 1. Times is 3. So times minus 1 is 2. Now, here's where the confusion would come, because then I would jump back up and do la la la. Instead of doing that, let's do this. Boom. Look at this. A fresh copy. What is num? 3. What is times? 2. Okay, because we called it again. Is times equal to 1? It is not. So, return num, which is 3, plus my mult num, which is 3, times minus 1. Times is 2, so times now becomes 1. Okay, so where do we go with this? Bang. We have a whole new copy of it. This is exactly what's going on in your memory. Okay, and when we've recalled it, we have num. We have times is 1. If times is equal to 1, is times equal to 1? Yes, check, it is. So what do? We return num. What is num? 3. Okay, so you're saying, where do I return it to? You return it to where you called it. So this entire operation here is a 3. So now this function is ready to return. Return num 3 plus 3. What's that? 6. So I return 6. Where do I return that to? Right here where it was called. Okay? I do that. That's a 6. So now I return 3 plus 6. What's that? 9. That's the answer. Where does that get returned? That gets returned to the calling function right here. So the value 9 is put in A, and when I print A, I get 9. Okay? If I did 4, what would happen? I would call it again, and I would add another 3. You'll notice as you go, and we call this going up the stack, because you're pushing and popping. You're going to learn what that's about in Unit 6. As you go back up this ladder we've created, every time you do it, you're adding a 3. Okay? So if we went and created a 4, you would just do it one more time and add the 3 again. And if you think about it, that's all multiplication is. It's addition on steroids, yeah? Okay, that looks like a mess right there, but you understand it because you were there at the beginning of the trace. That is all recursion is. Yeah, it refers to itself, but it's not a big deal because it's a fresh copy. You're not digging down or using the same thing for different variables. You know what? My variable used to be 5. Now I have to say it's 4. It's a fresh copy. It's just like this, what's in front of you. It's a fresh copy. Okay? I am also going to put multiplication recursion up on your Sakai site, so you will have it to play with. And I beg you, please, play with it, play with it, play with it, play with it. I'm getting into a part of my research now where I'm trying to structure failure, because that's how we learn. We mess up, and then we have to correct things. And if you can learn from failures and correct things properly, then you will learn quicker and better and deeper. And we're calling it scaffolding failure. And you've got to fail. You've got to do things wrong in order to learn how to do things right. Nobody does anything perfect on the first try. Okay? So how you learn and your facility with these kinds of things is directly based on how many times you try things and mess up. mess up, get things wrong. We're wrong all the time. Okay? I probably think my failures are more important to me than my successes. Because your failures is how you learn. It's how you move forward. It's how you gain experience. Eventually, smarts and experience comes together and it turns into wisdom. Okay? So, you got to get there. You got to practice. You got to practice, 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 practice. All right? This stuff's going to be on Sakai, so you have no worries. So, plus, you know the deal. This is a YouTube video. Stop it. And you look and trace and copy and do whatever you want. Coffee. I'm procrastinating now because when I'm done with this video, I got to go out and shovel. I'm going to do the first round of shoveling. Get all the crud off my Jeep. Maybe I'll go to the supermarket. I don't even know if they're open. I go to the Stop and Shop on Route 1 over there by the Applebee's and the McDonald's. Got to stay away from those places. I'm a chunky monkey, but if I ate over there, I'd be, goodness gracious, you wouldn't be able to take me over certain bridges. I wouldn't be allowed to get in the elevator. No. Bad enough I'm having spaghetti tonight. At least I'll have a little salad and tell myself that's okay. But I digress. Announcements. We're in pretty good shape. I have just begun to start grading the midterms. Hopefully I'm going to get them back to you next week. Kit and Qasim have done a wonderful job getting everything graded. I have your grades. I'm ready to send them out. I was wondering whether I was going to send out midterm grades with Unit 4 grades or Unit 3. I think I'm going to do it with Unit 4 grades because I've needed some extra time to deal with some nonsense at work. So I think what we're going to do is I'm going to spend a lot of time this weekend grading papers, and we'll do it with the Unit 4 grades. So Unit 3 grades, hopefully in the next couple of days, I'm going to take some time and shoot them out to you and get them back to you. People did very well. I'm very happy. The next time we meet, we're going to go over Harsh Ed and some different things that we did for that. And we're going to do some Q&A, and we're going to have some fun. And that's coming up, I think, because today's what, the 21st? So I believe the 27th is the day we meet, right? Well, I'll look at it later. So we have class soon because we always the last Tuesday of the month when we do the spring. So we're going to have class soon. So know that. Other than that, make sure you know what your groups are. Make sure you understand what's going on with the final project. Because the proposal, boom, 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 it's going to come up real fast. And you know what? We've only got 6 weeks left. The last day of classes is April 30th. Okay? We're going into that a little bit because I don't give exams. So we're going to use that exam week as time for you to do your final project, which you'll appreciate. But, I mean, it seems like we just got started. We did just get started. It's crazy how fast time goes. But we've only got about 6 weeks left. All right? And in those 6 weeks, you have wonderful Unit 5, which you're going to get to at the end of next week. You're going to love that. And then in a couple of weeks, I got a trip to Boston coming up. I'm going to PAX in Boston to see what the video game people are up to, because that's kind of what I study. All right. You should be good. I have got you the first video a week ago. Then you have this. Tonight, tomorrow, you're going to have the assignment. So with a full week to go, you'll have your Unit 4 assignment. Like I've said before, it's no grade checks. You'll be fine. Okay? The quiz is going to be Thursday. All right? You need to be ready for that. I forget what day it is. Hold on. I keep telling you all this stuff. All righty, Rudy. The 28th, which I think is the Wednesday. So your quiz is going to be a week from today. All right? So I better get you that assignment tonight. I think I'm going to do it tonight. All right? So what else do we have here? You got that in. That's okay. April 6th is when the proposals are due. That's what I wanted to look for. So you still have some time there. Go into those forums and talk with your people and talk with your group mates and get things together, and you should be okay. All right? Then I'm going to get out of here. I know this has gone longer than I wanted it to, but we haven't spoken in a while, you know? Spring break is over. The snow day is going to be over tomorrow, and it's time to get back going with Python so you can get straightened out. Everybody's doing pretty well, so I'm pretty happy. But Make sure those forum posts are long enough. Make sure you get things on time. You guys are losing little points here and there. And if you're a point or two shy of an A at the end, you're going to be upset. Okay? It's about detail. It's about attention to detail. It's about schedule. I know I'm blah, 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 verbal and send out announcements a lot. And I worry that they're going to turn into noise, but read them. All right? And I use them as reminders. I realize this is a hybrid course, and what it lacks that brick and mortar has is structure. So I want to try to provide that structure by constantly reminding on deadlines and kind of, shaping what we have to do and when we have to do it and providing structure that way. So that's kind of like my way of combating the lack of structure you may have with a hybrid. I've taken hybrids before. When you get done with a unit, you take a test, and they're like, okay, see you in 3 weeks. And you have to do all the material yourself, all the things yourself, with no feedback, with no talking, with no reminders for deadlines, with no anything like that. And I got it done because I'm a big boy, but I didn't like it. There was no structure. I didn't know my classmates. It was like a legitimate old correspondence course where you used to take courses by the mail. It was like, it was weird. It was weird. So I don't want that. I almost want to generate a classroom feel, but you don't have to pick up and go to class every week. You know what I mean? So I know I'm big with the announcements, but there's a method behind the madness. All right? All right. Again, I'm digressing again. I'm going to get out of here. You be good. I will talk to you soon, and I'll be doing announcements up until quiz day, which is a week from today. All right, I'll talk to you soon. Bye.